Okay, so I think I got this wrong earlier. I worked it out again on a whiteboard, and what we're going to go over is basically, let's say that we have a plasmid. Okay, this is a plasmid. And we have a gene, and we're going to call this gene. And what we want to do is let's call this G, let's call this P. What we want to do is we want to end up, so this is going to be a plus, equals, and we're going to get a basically another circle that's bigger. Okay, and this region is still G. So we're basically putting this into the plasmid. Now, this is actually a little bit trickier than maybe people that aren't super familiar with biology think. At least it was for me. So there are a number of ways of doing this. I think that the umbrella term for this is assembly, because you're assembling DNA together. The general, I guess, name of the method that I've been calling this is that the way we're going to do this is assembly via inverse PCR, and I'll explain what that means. I actually hate this name. I think it should just be called PCR, but I'll explain. And Gibson, which is just some dude's name. I don't really like named things, but as far as things go, it's not so bad. Okay, so the first step that we need to do is we are going to need to linearize. So this first step, step 1, linearize P. Now, I will say, I think you probably want to have already watched a video on PCR. I think you might be able to get away with not in this video, but some things might be confusing. So first off, this is mostly going to be a lesson in directionality, because the directionality of DNA is kind of the most important part about figuring out how to do all these things. Okay, so I'm going to draw a section of DNA. Okay. Okay, so we have a little section of DNA, and we're basically zoomed in to maybe a special spot right here. We'll call this X. Okay, and what we're going to actually call is we're going to say that there's a break point. So this is going to be the break point. Okay, and effectively what we're going to end up with once we linearize, so the result is going to be basically a big long, so this is P, but with an X here. So X is here at the start, and I guess you could also think of X as sort of at the end, depending on which side you choose. So anyways, let's get into how are we going to linearize this thing. Well, we know that if we heat up DNA, these two strands, so with heat, 95°-ish, these strands come apart. And one thing that I'll say here is what I should draw this as is that this is actually a loop. Okay, so let's keep going. Now, maybe I'll draw them sort of far apart. So, okay, wait, I actually want to define some notation. So, first off, I'm just going to define some symbols. So first we're going to say that that A is equal to 5 prime A cat. This is just going to make our notation a little bit simpler. And then I'm going to say B is equal to wait, hold on, let me think about this. No. Okay. We're going to define A as 5 prime A T G T T. So this section. So this is this section. Okay. Then we're going to define B as hold on. I think I did this wrong again. Hold on. Okay, so A No, that's right. That's right. This is going to be I'll explain all in a minute. This is turned out to be supposed to go way smoother. Okay. So wait. Jesus Christ. Okay, and then so that's here. Then B is going to be okay. So now I'm going to define a little bit of notation. So I'm going to say that notation X RC or RC of X is equal to basically the reverse complement. Complement of X. Okay, what that means is that if we have 5 prime X 3 prime, then, and let's just call this S, then SRC is equal to RC of S is equal to 3 prime at X 5 prime. Okay, so I'll do a couple of examples. So we'll write A, say RC of A. This is going to be 3 prime, and then we're going to do the reverse complement. So, and this is going to be the complement. Okay, so what do we have? We have a T at the end here, so we want A, C, A, T. A cat. So since we had A, okay. Wait a minute. So the complement, here, wait, let me just chill out. The complement of A would be five prime T A C A A. Then the reverse complement of A will be 3 prime T A C A A 5 prime. Okay, this is the same as writing. Wait, hold on. Did I mess this up actually? No. So then this is equal to 5 prime A C A T 3 prime. Okay. All right. Yes. I'm getting back. This is embarrassing. Okay. So let's keep going. So the complement of B is going to be what? Well, it's going to be this 5 prime T G A A C. Okay, then RC of B, we can just flip the numbers. So we're going to get 3 prime T G A A C 5 prime. And this is the same. We can just flip this around. It doesn't, the directionality is something that you're allowed to mess around with. So this is going to be C A A G T, I believe. Did I do this right? Let me look at my picture, because I did do this earlier, so I should get the same things as before. C-A-A-G-T. Okay, good. So this is 3 prime. Alright, so now that we've done this, I would like to... Let's see, can I select... I can only select as a rectangle. I wish they have an amazing erase tool where you can, like, select individual lines. I wish I could just do that. Okay, so let's erase this, and let's erase this, and let's see if we can move this out here. What? Okay, good enough. Alright, we lost some of the primes, but... Okay, so now we have our example here. We can always refer back to that. Okay, let's also select... Oops. Okay. Alright, so this whole thing was a really long way for us to do rewriting this string. Okay, and I guess I lost this. I don't know what happened. Alright, so now we can rewrite this. We have AACAT. We can go and look up in this table AACAT. So that's RC of A. So if we rewrite this, so this whole sequence S is also equal to 5 prime ARC. Okay, then we have our like breakpoint X, and then we have ACTTG. ACTTG. That's B. Okay, then this is 3 prime. Then this has to be BRC, 5 prime, and then this has to be A. Okay, so now, instead of having to work with all these letters and make it really complicated, all we have to do is now think about S. Okay, so our whole, we have a ring still. We still have a ring. But we have basically, this goes around, this goes around. It's still a plasmid. Okay, but now the point is, when these denature, when S denatures, okay, so let's say denature the plasmid. Okay, now what we're going to have is we're going to have 5 prime ARC B, 3 prime, and then we're going to draw some space in between here. And actually, I want to select this and drag it down more. Okay. And then we have 3 prime A B R C 5 prime. Okay, so these are denatured now. They're split apart. So what we want to do, the whole idea behind the primer design, the big idea with designing primers that will linearize and amplify the whole plasmid is going to be basically, we want, if something is going to attach to let's call this strand 1 and the strand 2. If we attach something to strand 1 here, well, then the right side is going to be the 5 prime and the left side is going to be the 3 prime. Okay? So what that means is that elongation is going to happen this way. And similarly down here, if something binds to strand 2, then the 5 prime is going to be on the left, and then 3 prime. So elongation is going to happen this way. Okay, so what do we want to do? We want to have the break at X, but we want to make sure that we're copying the whole thing. So let's just go back. And the punchline of this whole long-winded way of saying all this stuff that's is basically, we are going to want to make our primers A and B. So this is the 5 prime and the 3 prime, and this is the 5 prime and this is the 3 prime. So what's going to happen is, if we have this loop here, then A is going to go and follow the loop and come back here until X. So this is still X. Okay? Same thing here. We're going to have this loop, and B is going to elongate and follow this loop to here. So I'm going to see if I want to draw the other section out. It's probably a good idea if we draw the other section out. So, because this might not be totally clear. Alright, so what I'm going to do is draw a big circle here. Okay. So this, let's say that this is strand 1. Okay. Sure, it doesn't matter. We can do strand 1. So what we're going to say is that, so what does strand 1 have? Strand 1 is, S1 is equal to, oh wait, I don't want to draw it right there. Let's erase that. Just draw it a little bit above. S1 is, you know, dot, dot, dot. Well, let's say 5 prime prime, dot, dot, dot. And then it's going to have A, R, C, B, dot, dot, dot. And it's going to loop around. So, but this is still the 3 prime. But it still loops around. That's fine. So let's just do this. Let's call this A, R, C. And we'll have the outsides go counterclockwise. Okay, then this is our breakpoint X. Actually, I don't want to draw it right there. Let's close X. And then we're going to have B here, right? Because that's the other part of this. And so now we can draw an arrow, you know, 5 prime, 3 prime. All right. Now, what's going to happen when our A primer binds? Well, our A primer is going to bind here, and it's going to be the other direction. So it's going to be 5 prime and 3 prime here. And it's going to go around. It's going to go around. And what's going to happen here when it elongates? It's going to make BRC, because that's just how polymerase is going to work. It's going to add the reverse complement, because if we were to look at a linear slice of this thing, we'd have ARC, oops, can't see that, to B. Well, if we start at A, we copy it down, this is going to be BRC. I mean, this whole strand, you know, if this is S, then this is going to be RC of S. That's just how DNA works. Okay. But the point that I'm actually trying to make is we're talking about linearization, and we're sort of still going through this kind of annoying route of like, okay, yeah, so we have this thing of these primers, and then when we heat them up, you know, these strands denature. And I guess one thing that is probably worth saying is that when we talk about these loops, what's actually happening in reality is that we have maybe like a primer like this, and then we have another primer that's looped around it. So it's kind of more topologically constrained than this. But I'll show why this actually ends up not being a problem for PCR, and why we can rest easy. So the key reason ends up being that in here, so if this is 5 prime and this is the 3 prime end of this strand, there is no bond. So basically the important part, actually let's just do this. So DNAP does not add a bond between the first and last nucleotide. I don't want to use terminology. I don't like the terminology. Let's call it base. Okay, so that's important, because then let's think about what happens. Well, okay, wait. Let me draw the second circle. So this is going to be S1. So let's just draw the second circle so that we have an idea of what's happening. Okay. All right. Alright, so let's call this S2. Now, S2, what is S2? S2 is down here, and it has BRC and A. So let's just draw BRC, and then the 5. This is the 5 prime for the outside, so this is the 5 prime. Same with this one. This is the 5 prime. So we're drawing it counterclockwise. So this is gonna undo this line. Okay, BRC, and then this is going to be A, I believe, right? Oops. Yes, so BRC and A. So this is still X, or yeah, that's okay. And this is going to be 5 prime to 3 prime. So they're flipped, right? Okay, that's good. So what was our second primer? So wait, here, maybe we should say that these are our primers for okay, so I added a note up here. A and B. All right. So what's our second primer? B, right? Because we have BRC. So B is going to go here. Now B, because 5 prime is going counterclockwise, then the strand is going to have 5 prime here going 3 prime. Okay, so this is going to, again, it's going to wrap around, bring it around town, and here we're going to have ARC. Okay, and again, there is what's called a NIC. I don't know how you spell this, NIC or NICK, but basically it's the same as what we said up here. DNAP does not add a bond. Okay, now we finally get into why this causes linearization. So let's consider what happens here. Maybe I'll draw a circle like this. Okay, so we're going to draw an arrow here, denature. So before denature, let's draw a simplified picture. And a simplified picture would look like this. And again, I'm sort of ignoring topological issues. I wish they had a mode of the eraser that didn't just erase strokes, because okay, so there's a break. So that's at X. Now, when we denature, so, you know, denature, what's going to happen is basically we're going to get one circle. Oops, let's just do it. This one, and then we're going to get this one. So basically one of these is going to be linear and the other is not going to be linear. And in this case, this is if this was S1, then this is going to be RC of S1, which is going to be equal to S2, right? Oh, wait. So, okay, wait. This as S to the outside. And this is S2. So this is not right. This is S2. And then we have the reverse complement of it, and that's going to be S1. Oops. Okay, so we have X at the starting point, and what we're going to have here is this is B, the 5 prime, and at the end we are going to have ARC, 3 prime. Okay, nice. Now, I guess one thing maybe you could think about is like when these denature, you have a circle here, and you have like a loop here, but this loop is not connected here, right? So this thing could just like slide out. So it's not like not topologically looped or something. I don't know what the real word is, but they're not connected. They're not knotted together. So that's sort of one thing to keep in mind. Okay. The same thing is going to happen to this one. So here we're going to have the same thing. And I'm not going to draw the diagram again, but basically what you get is you get, so here, denature. And we're just going to take, okay, well, I'll just do this. S1 and then S2. And S2 is going to be, so S1 is going to be B, let's see, we can see from here. S2 is going to be A to BRC. Okay, now let's collect what our products are. So these products are going to be 2 single-stranded things. So we've just denatured, and we're going to have 2 single-stranded things. We're going to have 5 prime A BRC, and we're going to have another one, which is B ARC. Okay, so this is the single-stranded. These are not connected together. They're whatever, sitting in solution. But now the important part here is that how are we going to get, exponential copies? So the way that we're going to get exponential copies is that now, so right now these are different strands. Like these 2 pieces of DNA are like different sequences, but they are complementary. Wait. Yes, they are complementary. If you rotate, if you flip this one around, and they'd have to be okay, just because the original source was complementary. Okay, but now what are primers again? Our primers are going to be B and A, and this is going to be 5, and this is going to be 5. So this is going to go this way, and this is going to go this way, and then now we have 2 copies of identical DNA of the plasmid. And I guess I should just show that, because what happens is this is going to end up being ARC, and then this is going to be BRC. And so now we have, a strand. I mean, these 2 are equivalent if you just rotate them 180 degrees. Okay, so now we've done the first step of understanding how to, and wow, my drawings just get bigger and bigger. It's so funny. It's like it always starts really nice and neat and small, and then it just devolves into disgustingness. But, okay, so we've now basically, if we look at our tech tree here, okay, step 1, linearize. Okay, now let's start small again. Step 2, amplify the gene. Insert. Okay. Let's see. Is this the order in which I want to do this? So actually, I guess I want to talk a little bit about Gibson. So let's Gibson. So Gibson is not that complicated. And honestly, I'm not even like, it's not even worth me explaining because it's so basic. But basically, let's say you have two single-stranded pieces of DNA, and this region here is the same, or what they say is homologous. Now, basically, if this is a 5, this is a 3, this is a 5, this is a 3, and then this is a 5, this is a 3, this is a 5, and this is a 3, then there's an enzyme called exonuclease. Okay? And this eats back 5' ends. Okay, so basically this end is going to get chewed back and this end is going to get chewed back. And then what happens is you end up with 5, okay, and then a 3, and it's like that. And then you have, how should I draw this? Maybe it's like this, and this is a 5. This is a 3, and this is a 5. And really what happens is this also gets chewed back, and this gets chewed back. And that'll be important. But for right now, we just want to talk about the joining of 1. But what actually ends up happening is that we end up having this plasmid. Wait. We have this plasmid like this, and we actually have to do an insert like this, and then an insert like this. So this is our insert. So it has to connect in 2 places. And the fact that it chews back at all the 5' ends is important. It doesn't just chew back one of them arbitrarily. Okay. So let me just finish this drawing. So what's going to happen here is, so this is a 5, and this is a 3, this is a 5, and this is a 3. Okay, so both these ends got chewed back, but then these guys are designed to connect. And honestly, I would love to do some back of the napkin math to understand, like, for me, the whole idea of these homologous sequences seems totally far-fetched, because it's like, does the DNA really just like collide like this? And I mean, I guess it does, but it seems crazy. Okay, so all right, so is there something that I wanted to say? I guess one thing that I wanted to say back up here that I didn't really get a chance to say is that if let's say that DNA polymerase didn't make it all the way around. Let's say it only made it to like here. So DNAP fails to make it all the way. So if it fails to make it all the way, though, then basically this daughter cell, when it denatures again, is not going to have its end with ARC. And what that means is that the A primer that's in the PCR mix is not going to bind to it. And thus, this failed strand is going to at most produce a linear amount of... well, okay, wait, let's think about this. So it's got B on the center. Actually, I think that this can't produce any... I think this can't produce any daughters, because the primers we have are B and A. So no problem, because it has no way to amplify. And then same with this outer one. Okay, I think I was thinking of the outer one. So the outer one, let's say that this one fails here. DNA P fails. Well then, again, wait, hold on. Yeah, that's the same. That's the same. So we're good. All right, so we reliably have amplified the linear sequence, and now what we're talking about is how to join it. So the reason why I thought of that is that this can actually chew back more than you want, more than the homologous region. But this like master mix also has DNAP and ligase. Okay, so basically what's happening is that, let's say that we have now, so these go to here. So we have big long strand like this, and then a big gap. And then same here. So wait, let's see, how far does it need to go? So does it need to go to there? Maybe. And this is the overlapping region. Yeah, that works. Okay, so then this is the overlap. So then what happens is, if this is a 5, this is a 3, 5, 3. You always got to keep track of the directions. Well, what's going to happen is DNAP, they're going to come on here and add up all these until there's a nick. So there's still going to be a nick at the end. And same here. It's going to add in all this, but there's still going to be a, or I could just leave it as a nick. Anyways, then ligase comes in here. Ligase. All right, so then this is repaired. Oops, what just happened? What is going on here? How do I delete this? Just put it over here. All right. Okay, so the question now is basically, if we have, okay, so let's just take a representative of our, double-stranded DNA. So so we're gonna have, let's draw it like this. And then I believe this is BRC. Okay. And man, I have drawn this diagram so many times today. Okay, so this is our amplified linear plasmid. Linearized. Okay. So, okay, so what's going to happen is exonuclease is going to chew back B, and it's going to chew back A. So if we have our gene, so our insert here, 5, 3, 5. Let's zoom out. Well, what do we need? Let's just say that we want to connect these together. Then this section needs to be BRC, right? Because it's going to get chewed back, and then this is going to be B just by complementarity. And then this will, B and BRC will attach together, and we'll get 5 prime, big line, BRC. Actually, do I want to draw it like that? I don't want to draw it like that. I want to just draw it as a line. We'll draw it like this. And 3 prime. And then 5 prime. Basically, this section is BRC. Actually, how do I want to draw this? I want to draw this where, and this is B. So this was like that. So basically, this gets chewed back, this and this. Or rather, this and this come together. So B and BRC are together. Okay, but what's over here? Over here, still, this is chewed back and this is ARC, right? And so what do we want? This is chewed back as well. So we want, basically, this section is going to be ARC RC, which is equal to A. Okay. So that means we've just finally computed what the DNA sequence of our gene fragment needs to be, including the overlaps. And one thing that I'm doing that's a little bit nasty is that these symbols up here, A, B, you know, A complement, B complement, A and B reverse complement, is I'm kind of treating them as generalized primers and overlaps. So I'm kind of assuming that the overlap length is the same as the primer length, which I think might be janky. You know what I just realized I forgot? Inverse PCR. The reason why I don't like inverse PCR, it's they just, you take your hands, you know how in physics they do this weird thing like this? Just go like this or like this. So if you have two, like, hold on, you want it to be like this? I mean, I guess I'm looking in a different direction than you. So for you, if you draw the 5 prime, let's see. No. If you're drawing the 5 prime such that, wait, this is going to be confusing to do. So for me, the 5 prime is right here. For you, 5 prime is over here. Wow, that's crazy confusing. Okay, here's a better way to draw it. I'm just going to draw it on the whiteboard because we have a whiteboard. Okay, so inverse PCR versus PCR. It's literally just like if we have, how do we want this? We want, it's literally whether or not you go this way and this way, or you go this way and this way. So it's whether or not they point away from each other or not. So they're basically the same thing. Like, I don't know. Maybe it's not worth it to have a weird. Okay, so what is our insert? Our insert sequence is going to be. So what are we going to have? We're going to have BRC because this BR. Because, okay, we're going to write it as like a 5 prime BRC. Then G for our gene. So this is going to be G. And then here, what is this? This is A. This is A. So GRCA. We did it. So this is the sequence of the, basically, the overlap that we need. So if we take a I kind of drew this in a bad way. I'd rather draw it on the outside. I think it's better to draw it on the outside. But here I drew the primers on the inside. But I guess I prefer it this way. So we have A. Wait, this isn't right. Oh no, ARC, B, A, BRC. So we have our plasmid here with ARC. Yeah. It linearizes fine. So then this, I'm just trying to figure out, like, is this really gonna work? Because I need to buy all this stuff. All right. So, the last thing that we need to do is figure out. So we have so Gibson. Basically, the Gibson section is like, determine gene insert sequence with overhangs. Okay, then the last thing I want to know is, this is kind of the bad, I would have preferred to do it the other way, the other order, but figure out gene insert primers. So we have 5 prime BRC G A, right? 3 prime. Then we have 5 prime ARC GRC. Wait, is that right? I'll just leave that blank. I mean, yeah, it is. Okay. So these we can just like ignore. All right. So how are we going to do the primers? The primers need to go this way because this is going to be a 5. Whatever binds to this and whatever binds to this is going to be a 5 and this is going to be a 5. So we want them to go towards each other. This is what I was saying about inverse versus normal PCR. So if we want to clone this, if we want to copy and amplify this whole thing, then we don't want them pointing away from each other. We want them pointing towards each other. So what that means is that this is going to be BRC and this is going to be ARC. So the primers for, so in oh my fudge, conclusion, linearization primers. A, B. Gene insert sequence 5 prime B R C G A 3 prime, then gene amplification primers ARC and BRC. Okay, and one thing to note is that this we just order this from twist. Okay. So I believe that this should make sense. And it will work, but who knows? Wow, that was 57 minutes? Dude, I thought that was going to be like a 5-minute video. Okay, well, anyways, that's that. I wanted it to be short.